Hi, my name is Quinn, and I will be presenting uh, mine, Joe's, and Nathan's Lab 4 simulations, or at least what we'll be able to get to work of them. So I'm going to, so we start out here, um, and we make sure that our output 00 is turned off, which is our enable for our serial bus. And then we check to see if the clock is high, and if the clock is high, it reads in the input to the flag 00, waits 5 seconds. If it's high, it reads in the input, next flag. This is just a simulation of how a serial configuration could work. There's better PLCs to actually run stuff like this where you can just use bit shift, and you also have bitwise actual functions that you can do. Here we're very limited, so we pretty much designed it to read them in and then check if it's supposed to be a certain configuration, which is happens to be the number 0 with a uh, even parity, or sorry, odd parity. And then if it's not, if the parity flag's wrong, but all of this checks out, then it outputs here. Or if it's wrong period, it outputs here and turns on a light to let us know there's an error, and then it loops back around and tries to reset everything, tries to see if we can get it again. And then if it is correct, it makes sure that output 2 is turned off, and then it turns on output 1 to notify us that we got the correct thing, which would be the appropriate time to then go and shift out our data. But due to the just sheer complexity of it, we weren't able to do it. It's partially due to us actually running out of breadboards and stuff, so we couldn't even make shift registers, and we didn't have any in the lab to utilize. Now I'll run the simulation. So if I start the simulation, we can see that everything is off right now. So our clock is the 00, and our 1 is going to be our bits. So if I go to 0, if I click through this, it technically recorded our first bit there. It's not going to show a difference, but recorded the second bit. Now if I click and hold that input on and then click that, we can see that our input changed here, notifying that we have read in a bit, and then another bit, and another. Now if we go down to our outputs, we actually can see that our output 2 is on, indicating that we have an error. That light will stay on until we read the correct input. So if I go through again, it was wrong again. So 5 seconds. So then our correct combination would be 0. And then I have to hold that on to make it a 1. And it'd be 1, 1, 1. And then turn that off again. And because our parity check should be 0. And then we can see that our outputs. I will be moving over to the Logisim simulation next. If I put in that number, you can see it does a 5. Can't do that because it's not considered a number. It's higher than 9. There's the 7. And I think it went too high for me to see it. We'll try and hit the reset here. Yeah, so it should be 1010. If I hit that, you can see it shifted it up to here. I know that, let me slow the clock down a little bit so you can see a little better. So we're going to hit the reset here, which clears the register there, and then allows me to, it also reinserts it here and resets the clock. And then if I press and hold this, get the timing right, see that it reads in 7. And then it outputs the number over here. I'll do that one more time. So reset. Here comes number 7, Howard, and it outputs 1, 0, 1, 0, which is 5. So it's whatever you put in this register. I can make it even shift something longer if I wanted to, but I just thought 5 was a good number to shift. And that concludes the Logisim simulation. And now I'll move over to our I'm going to pause it and then move over to our assembly language part of the simulation. And now we're over here at our assembly language portion. So using code I could piece together and figure out how to do, I pretty much implemented shifting in a number through this UART. That number happens to again be 7, and then it outputs a message and says that's okay, that it's good because it has the parity bit. And again, that's being sent through serial. So if I go and hit run, then I go over here, and you have to input the brackets with it, because that lets the UART know that it's a hexadecimal value. And then 87H is the value we're looking for, which actually if I send this, so I'll hit this to transmit, it's transmitted. We actually can see our bit values right here. So it's a 1, 1, 1, 0, and 0, 0. And then this last bit, bit number 7, is our parity bit. And it happens to be even parity. So it's keeping the number of these even. So a little bit different, but that's just how it's programmed to work normally. And then as you can see here, it went through and then printed out 7 is okay. So it used serial and inputted, stored, and then compared to a value that was already in a register and then shifted out afterwards. And this was at the max baud rate we could do with this microcontroller. I'm going to run it one more time. So hit reset and then run. And then if I try different, let's try 8, see what happens if it does 8. Nothing should happen. So if I do 8, it reads in 8. We can see our value changed here.
9, we get the error because it can't check over 9, but all evens will work. And then for the PLC reading in our buffer, so if we have that running, so then if we give it the input of 0, 1, 1, 1, there's an error. So we need to 0, 1, 1, 1, 0, and then that will turn on this LED showing that the buffer is working and it is showing bidirectional. We just didn't have enough timer resources to finish it to prove completely, but our buffer is working and everything else.